Okay, for oblique asymptotes, it says in some cases the degree of the numerator is larger than the degree of the denominator. You could have oblique asymptotes. Okay, and you may have encountered this in advanced functions, so we'll look at it with an example. It says determine the oblique asymptote here. Now the reason why it says you may have oblique asymptotes and not that you will have, because it's not a guarantee, is typically what we will do is we'll just try to reduce this. We'll factor to see if there's any things that could possibly cancel out. In this case, nothing's going to cancel out because if I do some long division, then it's going to leave some remainder. So here, if I divide this in using my long division, I get a remainder of a -4, and I get the x plus 2 coming out here, which means that the way the function was originally written in this type of expression is equivalent to writing it this way. The x plus 2 and then my remainder of -4 of the x minus 1 types. And know that there's a restriction associated with it. Okay, so you did this stuff in advanced functions. But what that means is the following. It means that if I need to take the limit to investigate what goes on, let's say towards infinity, then taking the limit of the expression the way it was written is equivalent to taking the limit of the way that we've now rewritten it with that division statement. And what you guys would have encountered in advanced function is that whatever has shown up here, that's going to be my oblique asymptote. And also the remainder part here, as x approaches infinity, this starts shrinking down towards 0 because it's going to be using one of those building block type limits, the 1 over x types. Because as x goes to infinity, this stays constant. The fact that it's a 4 just means that it's going to be so small compared to the denominator. So this thing's going to start shrinking down to 0 and then not really play that much of a role. It plays a little bit of a role, especially when we're drawing it, and I'll show you that in a second. But this is the part that we're focused in on. That tells us our oblique asymptote. And again, you might have seen that stuff in advanced functions. So let's take this one step further and actually tell you some more stuff about this. What this also means is that if I use that exact same example and I wanted to kind of go further with this limit, then rewriting this in terms of the division statement would look like that. Using some limit properties says that I could say this. It's going to be the limit of this minus the limit of that. Well, I'm not going to be able to evaluate the limit of this because it doesn't really exist. But what this basically says is that my function is going to start tending towards x plus 2. And then this little remainder part, this starts tending towards 0, meaning it's insignificant. But as x approaches infinity, this piece here is going to start tending towards 0 from positive numbers, because this is positive, and then down here, because it's going to infinity, it's also going to be positive. So that's going to be important, because if you connect these two things, then what it's actually telling you is that my function starts tending towards x plus 2, but we're going to subtract a really small positive number from it as we kind of go along. And because we're subtracting something, that means we're actually a little bit less than x plus 2, which means we should be approaching this from below if we're trying to graph this. So I know as x goes towards infinity, as it approaches infinity, my function is going to start tending towards this oblique asymptote, but I know it's actually going to be at it from under, because it overall is going to start looking like x plus 2, but I'm subtracting a tiny positive number. So I'm subtracting something off x plus 2. So I should be a little bit less than it. Now if I start looking at the other side of it, towards negative infinity, I could say exactly the same thing, that it's going to tend towards x plus 2, but then over here, this section now, it's going to start tending towards 0, and because it's going towards negative infinity, the numerator is positive, the denominator is now going to start tending towards a big negative number. So that means this thing is going to start going towards 0, but I've got a positive divided by negative number, so it's going to be a negative number that I'm going to be subtracting, which means if I subtract a negative number, I'm really adding. So that means that towards negative infinity, this function is going to start tending towards x plus 2 plus a little bit because of the negative negative. I'm going to be adding a little tiny bit. So if I'm adding a little bit tiny bit, it's more than x plus 2. So this is actually showing it from above. So that's what kind of the remainder parts tell us. It gives us whether we're approaching from above or below, if you want to interpret it that way. So what this will look like, and it's by no means a complete graph, is that here is my y equals x plus 2 asymptote. This is saying as we approach positive infinity, I should be coming up towards the asymptote over here. And then this one's saying as I approach negative infinity, so on this side I should be approaching it from above. So below here, above here. And then we can fill in all the stuff in between when we put all the other pieces from this unit together. But that's how we deal with obliques.